Welcome back to Physics 141 Online. I'd like to work out a simple example of a problem where we look at a collision between two particles. Actually, this is not quite a collision, but it's the reverse of a collision. It's an explosion problem. A firecracker of mass m is thrown into the air. At the highest point in its flight, when it is moving in the positive x direction with a speed v0, it explodes. Just after the collision, one piece with 1/3 of its mass moves in the negative x direction with a speed v0 over 3. Find the speed of the other piece. All right? So you'll remember that when we have a system of particles that's isolated, an isolated system means that the sum of all of the external forces that act on all the particles in the system, if we add up all those forces due to external influences, that sum is equal to 0. And when you have an isolated system, then you can add up for all the particles in the system the product of the mass of each particle times its velocity vector. And so this is before the collision, and you find out that sum is the same after the collision. And so this qualifies then as a conservation law, and this quantity that is conserved is called momentum, right? Remember that P, the momentum of a particle that has mass m and velocity vector v, P is equal to mv. And so what we're saying in the expression with the summations over here on the right side is we're saying that when you add up the momentum of all the particles before the collision, it's equal to the momentum of all the particles added up after the collision. But remember, this is very important, momentum is a vector, which means that in conservation of momentum problems we have to keep track of signs and of directions. That's very important. It makes using the conservation of momentum law a little bit more complicated than using the conservation of energy, where energy doesn't have a direction associated with it. So let's now get some idea of what this looks like. Here's our firecracker, and we throw it into the air, and so it goes up like this, and it says when it's at its highest point, right up here, it explodes. So it's at that highest point, and it's traveling in the positive x direction with a speed v0. So it's a mass, capital M, according to the problem statement. It's traveling in the x direction, positive x direction, with a speed v0, and right there it explodes. So this is the picture just before the collision, or the explosion. Actually, it's an explosion problem, but you'll realize that explosion problems are simply collision problems in reverse. So that just after the collision, what we're told is there's a piece that actually ends up traveling backwards, because when it blows up, apparently the impact of the explosion shoots one piece back to the left with a speed v0 over 3, and it says that piece has 1/3 the mass, right? So it's 1/3 the overall total mass. And that means that there's another piece over here that has 2/3 of the mass, and we want to know what its final speed is. Before we even get to that point, we should think about how we should draw the velocity direction. And it's very important that we make sure that we draw it in a way that's consistent with the law of conservation of momentum. Now let's just look at the initial momentum vector, m times v0. It's in the x, or the I hat direction, so that the total momentum after the collision has to also be in the positive x hat direction. So the only way that this 2/3 m fragment can travel is to the right. It can't travel upwards or downwards or have any upward or downward component, because if it did, there would be some y component to the momentum after the explosion that would not be present before the explosion. So just by qualitatively looking at the situation, this v final, which is what we're trying to find, we know it has to be horizontal and it has to be to the right. So hopefully that makes sense. This is just after the collision, and that's often the way that these problems are set up. We want to look at the instant just before and then the instant just after. Of course, if we were to follow this a little further, both of these fragments would fall toward the ground in some kind of parabolic trajectory. But we just want to look at this instant just before and just after. So we have written down the picture. We have identified this problem and interpreted it as a problem involving conservation of P, because we know that it is essentially a collision/explosion problem. And now let's set it up. All right, we want to now develop a plan. So what we do is we write down the sum, right, of m times v for all the pieces before the collision. This is the before side, and then that will be equal to the sum of those products, m sub I times v sub I, for all the pieces after the explosion. So on the left-hand side, the before, it's easy. There's only one piece. All right, so we don't even really have a sum. It's just m times v0. And since velocity is a vector and this is in the I hat direction, I will just put that in. mv0 in the I hat direction is the total momentum of the system before the explosion happens. What about afterwards? Well, here I've got one piece that moves off to the left, so it's 1/3 times the mass, capital M, and its speed is v0 over 3. It's in the negative direction, right? So I can put in v0 over 3, but remember, it's in the negative I hat direction. Then there's the other fragment, plus 2/3 m. It has to be 2/3 because 2/3 plus 1/3 equals 1, which is the total mass initially before the explosion. So it's 2/3 m v final, and we know it's to the right, so that's in the positive I hat direction. So let's take a look at what we have here. We've got mv0 I hat, and then we've got this negative 1/9 m v0 I hat, right, plus again 2/3 m v final I hat. And so let's take this negative term and add it to both sides. We're going to add 1/9 m v0 I hat to both sides. So on the left hand side we get m v0 I hat plus 1/9 m v0 I hat equals 2/3 m v final I hat. So on the left hand side, 1 plus 1/9 is 10/9, right? So this gives us 10/9 m v0 I hat equals 2/3 m v final I hat. We're solving for v final. We're just about ready. Actually, we're in the evaluation step right here because we've plugged in the individual momentum components before and after. And so we want to divide both sides by m. The mass term cancels out because it's common to both. And what this gives me, if I multiply both sides by 3/2, it gives me 3/2 times 10/9 v0 I hat equals v final I hat, right? So a solution to this, let's see, 3/9, there's going to be a factor of 3, so it's 5/3. So this ends up being 5/3 v0 I hat. So the final speed, vf, we know the direction is to the right, so if I wanted to just answer the question the way it's stated, the speed v final is 5/3 v0. And we can check this two different ways. We can say, first of all, yep, it makes sense because it's got the right units, because we want a velocity, and we end up with v final is some numerical value, 5/3, times a velocity, so the units work out. And it also makes sense that it's a little bit larger than v0 because it has to end up with total momentum in the x direction being the same as what it was originally. And since the fragment 2/3 is less than m, right, 2/3 m is less than m, the final speed will have to be greater than v0. All right, so it's, v final is greater than v0 as expected, so I'll put a check by that as well. So this is a collision problem, but it's really an explosion problem. But explosions and collisions, if you had an explosion like this and ran it in reverse backwards, let's say you took a video of this and then ran it backwards, it would look like a collision problem. So collisions and explosions are just very similar. The only thing that's different is the time is running in the opposite direction. So hopefully this is helpful. You can see, again, the importance of taking into account the vector nature of momentum, because the fragment that went to the left, we put in the minus sign in terms of its momentum, and that kept track of the momentum as a vector. If we hadn't put that minus sign in, we would have gotten the wrong answer. So momentum is a vector. That's very important to keep in mind as you work out conservation of momentum problems. We'll do some more in class. I hope this is helpful. Bye-bye.